Very good morning, everyone. So, I welcome our speaker for the day. It's Snavya Sai Munti Murugu, and we'll be starting in about 10 to 15 minutes. So, ask whoever is there to join fast. We'll be starting the session. Oh, you joined using her college email ID. But I don't see a request. There is no request. Try logging in again. Nothing yet. I just introduced and waiting for others to join. But I gave you access now. Did you accept? But it does not show me any request. Because I would have given access, no? Yeah. No, not yet. Diana hasn't also joined yet. Nilesh is there, the speaker is there, and few from your departments, they're there. Yeah, I guess you get the access now.
Hello. Good morning, everyone. Shall we begin?
Yeah, hi. I think we can begin if people have joined.
Yes, ma'am. Sure. So, a very good morning to one and all present here. Today with us, we have our chairperson, Dr. Pramod Kumar Nayak sir, our esteemed faculty, and all the future innovators in this virtual room. We are here today. It's not just because we are interested, but we want to know what our future is. Today, we will have an introduction to a future world of quantum machine learning. Before we begin, let's know what it is all about. Think about how far the classical computer has brought us till now: self driving cars, voice assistants, medical imaging, space exploration, and whatnot. But imagine there is a problem that is so enormous, so complex with the data set that the supercomputer itself is taking a pause and struggling to find it out. To solve this, here comes the quantum machine learning. It's not just an upgrade, but a revolution. To lead us down into it, who else can do better than one of a kind? So we are here with our guest, Sanavya Bai Badri Prasad, who is a proud alumni of Dayanand Sagar University, who's making waves in Arizona State University, pursuing her master's in data science. She's here today to share the edge cutting device technology and what she's been working with us today. The agenda for today is we are going to kick with the things that is into quantum computing. And but it's not just the beginning. Let's highlight today's session with a live demonstration with truly impacting project that she has begun, that is classifying breast cancer using deep learning and quantum computing. You'll get to see that her team has achieved impressive accuracy of 93.8% in quantum model, and how these results are going to stand up against the classical machine learning approach. In this session, it's just isn't about learning new concepts, but about imagining the future with problem solving. I will encourage you all to stand and stay curious, ask questions, and learn a lot of things. So here to Sanavya, ma'am, you can take over.
Hello, everyone. A very good morning. First of all, thank you, Sri Devi, for that introduction. As you all know, I'm Snavya, so I'm doing my master's in data science here at ASU, and I'm a proud alumni of Dayanand Sagar University, batch of 2023. So let me just, I think we can dive right into the workshop. Just give me a moment while I share my screen. Is my screen visible to everyone?
Yes, ma'am. Yes, ma'am, it is.
You guys don't have to call me ma'am. I'm a student like you. Okay, so let's. Okay, so let's begin with the agenda. Like it was already mentioned, I would go into the introduction of quantum computing. What are the different gates that are there and the key concepts of quantum computing? We'll also look into the IBM Quantum Composer. I'll just show you a few demos and also show you the Qiskit programming using Jupyter Notebook, basically where we use the library, and then a little bit about the quantum machine learning, and then I would just brief you guys about what I had done for my project, and at the end we would have a discussion or a Q&A. So if you guys have any questions in between, you guys can drop it in the chat and I will try my best to answer it. So let's begin. So So, what exactly is a quantum computer? So, it's a machine that performs calculation based on quantum mechanics and not classical mechanics. And it basically studies the behavior of particles at subatomic levels like electrons. So now let's go into what is quantum computing. Like I mentioned, here we rely on quantum mechanic concepts. So few important concepts would be superposition and entanglement. So to understand the quantum phenomena, it is very important to understand a component called as a qubit. So let me explain what a qubit is in the later slide. So this is a bit about the history of how quantum computing has evolved and who are the people who are quite responsible. As you see, these three are the main people where Shor, Grover, and Deutsch are the three main people for quantum computing. So that's just a little bit about the history. Now, moving into the quantum mechanics, like I mentioned earlier, that we study particles at a subatomic level, such as electrons. When we go to subatomic level, we basically study the wave nature of them and not the particle nature of them. In classical, we look at the particle nature, basically things that we can see, but in quantum, we look at the subatomic level. Um, now, again, this is basically what I just mentioned. And in our normal physical world, we take the position and state of the object to be well defined and independent of each other, which is basically opposite of how quantum mechanics works. So a particular wave function of a particle can give us the probability of finding a particle at that point. And when we find the particle at a particular point, the wave function basically collapses, and that's how we measure it. Now, moving on. Like I mentioned earlier, there are a few key concepts, which is superposition, tunneling, entanglement, Heisenberg uncertainty principle, and energy quantization. So, like I mentioned earlier, there is something called as qubit. In classical computing, I think we're all aware of a bit which exists in either state 0 or state 1. Whereas when we come to a quantum, a bit can exist in both state 0 and 1. That is what a qubit is. And coming to superposition, we say that the particle can exist in all possible states at the same time. So as you can see in this image here, you can see a combination of the qubit 0 and the qubit 1. It's basically superposition. You can imagine it as a soup of all states. Next, going to quantum tunneling, this is another concept where it tells you that quantum particles can cross barriers by going through a barrier. So this can be visualized, let's say, for example, we throw a ball towards a wall. In classical physics or classical mechanics, we typically would say that the ball would bounce back. But the quantum mechanics tells us that the ball can be found on the other end of the wall as well. So as you can see, before the barrier, the wave function is basically having a high amplitude. So there are good chances that we find this particular particle before the barrier. And inside the barrier, the wave function obviously decreases. So the chance of finding at the beginning is higher than when the barrier ends. So after the barrier, the wave function basically remains very decreased, means there is very little chance of finding it. So this is based on how the wave function works and amplitude. So a higher amplitude means a higher probability of finding that particle. Moving on to quantum entanglement. So this is also called as something as spooky effects. So let's say you have two qubits, and we would say that they're entangled to each other when we can determine the position of one qubit based on the other. So let me just read this out for you guys. So it defines the relation between two particles separated by a distance. The relation defined by the interaction. So when two particles are entangled, one particle will be observed spinning upward and the other would be spinning downward. So this means that they possess properties which are correlating to each other. So to better understand this, let's just quickly watch a video on quantum entanglement so that you guys get a better idea of this. Let me know if you guys are able to hear the audio.
No, ma'am.
You guys can't hear the audio?
No.
No, ma'am, we can't hear you.
Okay. I'm not sure. Let me just stop sharing and share again. Just give me 1 second. Okay. Is it audible now?
No, not yet.
No, ma'am.
It's still not okay. I am not sure why the video is not playing. Given audio access to it. Okay, I'll do one thing. Maybe I'll just paste the link in the chat so that you guys can watch it later since the audio, there's some issue with the audio. Okay, so let's quickly continue. Okay, so if I had to explain entanglement in simple words, let's say y is equal to minus x, and if x is equal to 1, so y would be minus 1. So as simple as if the spin is up for x, the spin would be down for y. So that's when we say that two particles are entangled, and knowing the position of one particle, we can determine the position of the other quite instantaneously, no matter how far the distance. So this is one concept which is very useful as it allows us to explore multiple states at a particular given time. And one of the key features as to why quantum computing is quite faster compared to classical computing. So these two concepts of superposition and entanglement are very important. Now, moving to Heisenberg's principle, we know that you cannot know the measure and the momentum of a particle at the same time. So here, the wave function of a particle basically, as I mentioned earlier, contains all the information about the position and the momentum. So the amplitude tells us the position and the wavelength tells us the momentum. So when we square the wave to find the probability distribution, so that's how we can determine what is the probability that where a particle is positioned. And this is another concept which is important. You can just skim through this. Once this is done, I will just move on. So this is another video that you guys can watch, which basically summarizes all of the things that I mentioned in a videographic way. So I will paste the link of this as well in the chat. Okay, I will do it. Now, moving on to the representation of data, like I mentioned, I would come to qubits later. So a bit of data in a quantum circuit is basically represented as a qubit, and this is how you denote the data. There are two notations which is called as ket and bra notations. I'm not going to go into like the deep dive of that, but that's how you can represent the qubits. As you can see, this is how, let's say this is state 0 where the electron is in the inner circle, and then state 1 is just the outer orbit. This is just a physical representation of how they would look. And when I say superposition, like I mentioned, a single qubit can be forced into superposition of two states or more by an addition of the state vectors. So this is how the superposition formula would look. So I would give a simple example if you want to visualize how superposition works. Let's say you're tossing a coin, and in the air, you know that a coin can be heads or tails, and you do not really know what's the probability. You know that it's a 50-50 chance, but you do not know until you collapse the coin. That's when you measure the state and you know the value. But when it is in air, you can represent it as basically being in superposition. So that's an example that you can think of. So as you can see, this is another representation. This is basically in state 0, and then when I do superposition, you can see that it is in both the states. And this is just a representation for a 3-qubit register. Now, moving on, so like I mentioned already, when you measure, that's when you know what the outcome is. Until then, for a single coin flip, it's a 50-50 split, and then once the coin collapses, that's when you know what the value is. Let's move on to the next. I just want to quickly ask if you guys have any questions until now. Anything, am I going fast, or is there anything that you guys are not able to understand? You guys can let me know. If not, I will move ahead.
It is all fine when you can continue.
Okay. Let's go to the next important concept, that is quantum gates. So we all know that even in classical computing, we have like logic gates, which are like NOT gates, AND gates, NAND gates. So similarly, even there are multiple quantum gates that exist. So this is just what I just told. So let's look at one of the most important gates. So as I mentioned, there are two important principles, superposition and entanglement. And one of the most important gate to put a qubit into superposition is called as the Hadamard gate. So this is one of the most important ones. And this is just a lot of math as to how each, for example, how 0 is notated and how 1 is notated, and what is the final representation after you apply the Hadamard gate, which is a combination of both 0 and 1. So this is just another way of putting it. Simplest gate which involves 1 qubit and is called the Hadamard gate. Next, going to the NOT gate. The NOT gate basically reverses the value. So if it's a 0, then when you apply a NOT gate, it becomes a 1, and vice versa. If it's a 1, then it becomes a 0. So that is the NOT gate. The NOT gate is what is existent in the classical computers. So similar to the NOT gate is what is called as the poly X gate. In the quantum computers, it performs the same function as that of the NOT gate. Moving to, I would come to the Z gate first. So Z gate basically shifts the phase of a particular quantum state. As you know, the poly X gate basically inverts the state, so from 0 to 1 or 1 to 0, whereas the poly C gate only changes the phase. Now, what does a poly Y gate do? A poly Y gate is basically a combination of X and Z. Basically, it performs a phase shift and also a value shift. So that is what a poly Y gate does. We would look at how these seem when I go into the live demo. So for now, just understand. So these are a few other gates like S gate, T gate. I'm not going to go into the depth again. So this is another very important gate, which is called as the control NOT gate. This is the gate which is required to get a quantum qubit into entanglement. So we would need two gates, which is the Hadamard gate and the control NOT gate, to put two qubits or into a state of entanglement. So this is just how it is represented. This is how a control NOT gate looks. Now, moving on, once we've seen the gates, there is quantum algorithms. So there are two important algorithms. One is the Shor and Grover. So I mentioned that there are three important people who came up with this entire evolution of quantum. So one of them is Shor. So basically, Shor addressed the problem of prime factorization. With classical, it would take this much amount of time, whereas with quantum, it's drastically reduced, which was at exponential speed. So this is what his algorithm came up with. It's capable of factoring very large numbers in basically polynomial time. And this is just a little more in detail. I would share the slides later so that you can have a look at this. Another is the Grover's algorithm. This is basically like searching for an element in an n-dimensional array. So in classical, it would typically take O of n, where you look at every possible outcome, whereas in quantum, it reduces to O of root n time, where you can look at multiple possibilities at the same time, which significantly reduces the time of computation. So this is another important algorithm. Once, so we're done with the theoretical part of the session. Let's move on to the hands-on session now. I would paste this link. You guys can go ahead and create your accounts on IBMQ, so you can sign up and sign in with any of these options. If you do it with sign in with Google, you do not have to verify. And the free account gives you access for up to 30 days of using their services. And after 30, once you add your credit details, it would basically be a pay-as-you-go model based on the resources that you use. I will just quickly paste this link in the chat. So you guys can go ahead and it is very straightforward. Just open the link and click on sign up, create an IBM account, and then set up. So now let's move on to so this is how the platform would basically look like. And I would take you to one place, which is the Quantum Composer. Do you guys want me to wait while you guys set up the account, or do you guys want me to continue? Or I can just give you like 5 minutes so that you guys can have your account set up.
Yes, 5 minutes would be better.
Okay, yeah.
fine, fine. It's getting recorded. Yeah, yeah.
You can continue now, Sylvia.
Okay, yeah. So, if you guys click in this three lines on the top, it will take you to something called as the composer. So you guys can navigate yourselves to this page, and this is what you guys would typically see. Now, this is basically called as a block sphere where you can basically visualize the face and where exactly it is placed. So this kind of tells you all of that. And this gives you basically the probability distribution. So I'm first going to go about showing you guys the implementation of the poly X gate, also similar to the NOT gate. So if you go here and let me just delete this and show it again to you guys. So when I go here and drag this NOT gate here, as you can see, my initial state is in state 0 because I have one qubit initialized. So when I drag this NOT gate, you can see that the state changes to 1 from 0. So this is a basic implementation of the NOT gate. And as you guys had observed, the face was initially, the line was pointing towards the top, indicating qubit 0. Once I've applied the NOT gate, it is changed to the bottom, indicating qubit 1. Now, let me just show you a little bit about how to navigate this as well. So I typically used to use this Qiskit library, and you can see how it is coded out. We also have the drag and drop option, and also the option where you can code out your circuits. Another option that you guys have is where you can do an upload of a CASM file, where you typically would write this sort of code or the code that is here and just upload it. So, and you would see the same circuit that is built. So that is a simple implementation of the poly X gate. Now moving on. So this is the implementation of the poly Z gate, which would basically do a phase shift. So initially, first, when I apply the HUD-MART gate, I will again quickly delete all of this to show you guys what happens at each step. So, like I mentioned earlier, that the HUD-MART gate puts a quantum qubit into the state of superposition. So right now, as you can see, it is at state 0, which is at a probability 100. Now, the minute I drag this HUD-MART gate here, you can see that the probability changes to 50-50 as now the probability that it exists in both state is a 50 and 50. Now I would apply the Z gate, which would basically perform a phase shift. It wouldn't change the state, but it would perform a phase shift. So as you can see, there is a change in the color of the line here. So that is what phase shift is happening here. So as you can see, there's a phase angle. Now, let's say I apply the Hadamard gate again. So this requires a little of computation to understand why you would get the value that I would be getting. So, and the last gate that I would add to measure anything would be this one right here called as the measure gate. So I would just drag it here and drop it. So now you can see initially I put it was in the state 0, then I applied Hadamard, which put it in a state of superposition. And when I applied the poly Z gate, it did a phase shift. And when I applied the Hadamard gate again, it basically gives you an output of 1 all the time. So as you can see, the probability is 100. So when you compute this mathematically, you would understand why you would always get a 1. And as you can see here as well, the phase angle is changed and the probability is 1. So you guys can quickly try implementing this drag and drop feature, and let me know if you guys have any doubts as well as we go along. And as you can see, the code keeps changing every time I drag and drop a particular element. Let's go to the next gate that I mentioned, which is the Y gate. So it basically performs a phase shift and also changes the state from 0 to 1 or 1 to 0. As you can see, I just dragged the Y gate here and it is changed from 0 to 1, and you can also see that the phase is changed. So that is what the Y gate does. It basically performs a combination of the X and the Z gates together. Now that we are done with the basic gates, I will talk to you guys about the superposition, which I basically already mentioned. So here I'm just taking 2 qubits instead of 1, and I'm applying a Hadamard gate to both of the qubits. So this puts both of them in the state of superposition, and I'm just adding 2 measurement gates here. So as you can see, it is 2 per 2. So basically there's a probability that it can exist in any of these 4 states, and it is close to around 25 each. So that is what superposition does. Next, going on to the last one, which is entanglement. So entanglement is a combination of the Hadamard gate and the control gate. So the control gate basically flips the state of the second one. So this is what I'm doing. I apply the Hadamard gate to qubit 0, and the control gate linking the qubit 0 and the qubit 1, and I'm adding the measurement gates. As you can see, it can either be in a probability of 0, 0 or 1, 1, and barely any probability of 0, 1 or 1, 0. As I told, if the state of 1 is spin up, the other would be spin down, and at the state of 1, and vice versa. So that's how it works. And since I have measured it, it just collapsed to the state of 0, 0 as I've added the measurement gates. Otherwise, it would basically be in a probability of either of these 2 states, and very low probability of these if there exists. So these are basically the 5 implementations that I showed you all. You guys can maybe quickly try this out. I'll give you like 10 minutes to just implement these, get a feel of how they work, and then we can move on to the next part. Does that sound good?
Yeah, sure.
Yes, ma'am, there is one thing. As I created the account in this IBM cloud, then it asks for creating an instance. I created the instance. So, how do
Okay.
you navigate to the composer part that you are just showing?
Okay. So I think you're on this page,
Yeah,
right?
yeah,
If
yeah,
I'm
yeah,
not
yeah,
wrong.
yeah. Yes.
Okay, so this is basically a free instance which gives you access of 10 minutes. So what you can do
Okay.
is, if you can see these three lines on top,
Yes, ma'am.
just click on that, and then you can see a composer at the bottom.
Yeah, got it, ma'am. Thank you, thank you.
Yeah, you can go to composer. So you guys can take like 10 minutes, just explore the setup, and then we'll continue. So I would just like to add one thing. Once you guys have created the instance, you guys also have an option where it says setup and run. So you guys can just click on this. So these are basically the backends that are available or called as quantum processing unit. So just see which one is free and then just click run circuit, and you can go to this view job details page to see how the job is getting executed. So it just gives you all of the details where it is created, what the circuit is. Okay, sure. So as you guys also saw the set when I did the setup and run, you guys could see what the output was, and it basically just showed you. I just quickly pull that up and show it to you guys again. So this is the job that I had executed, and you can see it basically gives you the entire details, and you can see the result with each of the outcomes. This shows you the diagram, which is basically the circuit diagram, the code in CASM, and the code using Qiskit. So, and gives you the detailed logs so that you guys can keep a track. So, this is how you can set up an instance, select one of the available backends, and run the job and see what the results are. So once we are done with that, I would also like you guys to have a look at these main things. Again, to navigate to this, you guys can click on the three dots and go to the documentation part, which will take you to this get started overview and quick start. So if you guys go here, it basically tells you how you guys can, install the Qiskit library and run it on any platform like Jupyter Notebook or Anaconda using Google Colab. So this basically gives you a step-by-step guide as to how you have to go about it, how you guys can build your circuits. I'll also show you the implementation that I have done, and I will share the IPYMBY with you guys. Or you can also go ahead and click this download notebook that is right here. So you guys can just download this notebook and run it on any of the platforms that you guys want, and you guys would see the similar results that you all saw on the interface. So, for example, this just shows applying HUDMART to one of the quantum states, and then you're measuring it, so you can see a probability of 0, 0, and 1, 1, because we have put this in a state of entanglement by applying the controlled NOT gate. And as mentioned earlier, you would see either one of these two states. So this is one place where you guys can go through the documentation and learn step by step. There are a lot of resources directly available on this IBMQ platform. Now, another place where you can also look at is the tutorials. So when you guys go to this hello world part, it tells you again a little more deep dive into how you can run on the quantum hardware, like how you can get your API token, save that API token, and access the quantum hardware on your system. You can also use something called as a quantum simulator, which acts like a simulator and simulates. You don't really have to wait for the hardware to be available. You can use the CASM simulator. That is an easier way of going about it. So this hello world thing gives you a step-by-step guide as to how you guys can implement it. I will just show you my implementation as well. What basically, yeah. So I basically installed all of the necessary packages that they have mentioned, and basically just imported the necessary libraries. And here you can see, so there have to be two registers. One is the quantum register and one is the classical register. So I'm initiating both as 2 and 2. And then this is basically how it would look when I kind of visualize it. So we have two quantum states and two classical states. I'm applying the HUDMART gate to state 0, and you can see how it is visualized. And I next apply the control NOT gate, and this is how it is visualized. And now I'm adding the two measure gates. So the classical bits are basically used for measurement. So the equal number of quantum bits and classical bits are supposed to be present. So this is just an example of how you guys can use Qiskit on your local device. And now running it on the hardware and the simulator, it is one of the same ways, like I mentioned, you guys have to get the token. The step for the token, usually you can create the API token when you create an instance. There would be a button as create your API key. So you guys can go ahead and create an API key. And each instance has something called as a CRN. So when you hover over an instance, you get the CRN number. So you guys can copy that and paste that. So this is basically connecting your local device to the quantum lab. Now I'm again importing the necessary libraries, and this is basically where I'm telling I want to use the Qiskit runtime service, and in the same way I'm just defining the circuit. So this is how you run the job using the actual hardware. As you can see, I was running this right now, and because there's probably no hardware available, it is taking quite some time. Whereas when you do this simulator version of it, it is pretty fast and it gives you the result quite instantly. Let me just stop this and run this. You guys can see how quick using a simulator is. So that is better if you guys are working on either little complicated stuff, as it would take a lot of time on actually getting the hardware. If you guys are just doing simple experiments, then you can also try using the hardware. So as far as what I know, you guys have free access to about 5 qubits on the hardware for the free trial access. And then if you want to use more qubits, then you have to pay for it. So this is a simple implementation of how you can do it on your local device and get the same results as what you guys saw on the composer. Any questions until now, or are you guys stuck at any point and you guys want some help?
Yes, ma'am. After running that in the composer, you said to use
Mm-hmm.
setup and run.
Correct, yes.
Yeah, so it's still showing in progress. The
Oh,
diagrams are there and the
uh-huh.
code, but nothing in logs or in the diagram part is there.
Just do one thing. Sometimes the page, just refresh the page and see if the job is completed once.
Oh, yes, ma'am. Yeah, 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 yeah. Yeah.
Yeah, sometimes that doesn't happen. So guys,
Okay.
just refresh to see if the job is completed. So you guys can play around with all these gates, and like I mentioned, there are a lot of information. I know it's very hard to process it at one time. Even we all struggled during then, but at the end of this workshop, or maybe by tomorrow, I will send you guys a bunch of resources that I had referred to, YouTube lectures and books that you guys can read through to understand it in depth. It's going to be confusing and you guys might lose your minds, but that's how quantum works, really. You guys can take maybe 5 or 10 minutes to go through this documentations as well to see, and maybe you guys can download the notebook and quickly run it to see how it works in your system. Maybe the API thing might take a little time, but just doing the normal Qiskit one, I think you guys can try that out, which is there in the documentation quick start part. You guys can just try this out and visualize how it looks. So once you guys are done with that, we'll move on.
I guess we can continue. Is everyone fine with it? Hello.
Yeah, if you guys are done, then
If everyone
we
is
can
done, then we can continue.
if you guys can just respond by texting on the chat or something, that would be good, guys.
You can continue, Sana.
Okay, yeah. Let's move on then. So I think now that we have looked into the key concepts of quantum and also doing this live demos and the quantum composers and also seeing how you can use the Qiskit library in your local device. I think the last part of the section would be going through the project that I had worked on. So, what we basically did was a comparative study between quantum computing and classical computing for breast cancer detection. So, the data set that we used was the Wisconsin breast cancer data set. So, this is a very uh, widely used data set and a very well known data set. So that is why we chose to go with this. And we also wanted to do something in the healthcare domain, which is why we chose breast cancer as our problem statement. So this basically includes like 569 breast tissue samples collected by patients, and it has like 30 features, and the label would be either benign or malignant. So those are the two outputs. Let me just show you guys how the. So this is where you guys can find the Wisconsin breast cancer data set. You also find it on Kaggle. This is the official repository for it. So it gives you detailed information about how the features were collected, what was the procedure to get all the data. So you can see that it was computed from a digitized image of fine needle aspiration. So that was the process that they had used. And these are kind of the features that are present. So like I mentioned, there are like 30 features. So radius, texture, perimeter, smoothness. So these are the various features that would, kind of help us to identify if the tumor is benign or malignant. So that is about the data set. You guys can explore it. I will drop the link in the chat as well. Now let's go. I will just quickly pull up my report so that it's easier to show you guys what we had done. So basically, we had four tasks, you can say. Our first task was to implement this data set using all the classical algorithms. So these were like the 6 algorithms that we used. And for the same data set, we also built a neural network model, and then we know that we can improve the accuracy, basically tune the parameters and all of that. So this was the classical part of it, the machine learning and the deep learning part. And for the next task, we basically tested the data on VQC, which is a quantum circuit that basically combines the classical and the quantum part. It is basically like a neural network. So that is one of the basic quantum algorithms, which is known as variational quantum classifier. And the other one that we implemented was the QSVC, which is a quantum support vector classifier. And for the deep learning part, which is basically analogous to the classical part, we implemented QCNN to see how it performed, if it's better. Our basic focus was to see if quantum really has an edge over classical. How does it perform for such type of data? What are the key issues that we would face, and what are the improvements, or what is the future scope for it? So this is again just a description of the data set, what it is, what are the features, etc. So let me just quickly go into the methodology part for it. So the methodology is basically, I think this is the sample for every particular machine learning pipeline. So it is very similar where you have the data set in a CSV format, you do a little bit of data exploration, data pre-processing, and then you split the data set, you create the models, you evaluate the models, and we're just comparing the accuracies of different models. So this is just a little bit about what are the steps that we did in pre-processing, mainly like label encoding, normalization. So this is just a little bit about how we went about implementing the algorithms. The similar let's look at this block diagram for the implementation of VQC. Again, the steps are pretty much the same. The only thing is we would be leveraging the quantum principles to, kind of distinguish between features better, or also improve the time, and as the complexity increases, get like better evaluation. So that is where we try to leverage the quantum concepts. So like I mentioned, VQC is one of the algorithms that quantum machine learning offers. And one other feature that we did is basically dimensionality reduction. So why we did this, I mentioned that we have like 30 features. So for classical computing, we could use like all the 30 features and then implement the algorithms. But then for quantum, each feature would be mapped to one particular qubit. And like I mentioned earlier, on the free axis, we had like access to a limited number of qubit. So that's why we just stuck to 4 qubits, and we performed principal component analysis and did dimensionality reduction. So another main important thing is something called as feature maps in quantum machine learning or deep learning. So basically, we have to convert the conventional or the classical input data into quantum states. So this is done with the help of feature maps. There are various feature maps that you can use, but the most popular one is the ZZ feature map. So a variational circuit which is made up of layers, and you learn the parameters. So how we can alter the hyperparameters, we also have optimizers here, where you can tune it and improve the performance of the circuit. So this is one SPSA, and there's another optimizer called as Cobila. So these are like the two popular optimizers that you can use. And like I mentioned, we use 4 qubits on the IBM simulator and run our codes. Another algorithm is the QSVC. The process is pretty much the same. The additional thing is like the feature map that we have, because we have to transform the data into the quantum states and then apply the algorithms. Um, this is a basic CNN diagram where we build the convolutional layers, pooling layers. So those are pretty much very similar. So the input data, like I again mentioned, this is pretty much the same process for every particular thing. And this is implementation. I'll just show you guys the code in a moment. This basically talks about the results. If you guys want, I can also share our report and the paper that we have published. You guys can go through that to understand. So this is just a bit on basically what are the outputs that we got, what are the accuracies that we got. So we basically tested it on 3 splits, which was 75-25, 80-20, 70-30. So these are the various splits, and it shows the accuracies, precision, and the time taken for all the 6 algorithms that I mentioned earlier. And I'm just noting down which is the highest accuracy for each of the splits. As you can see, random forest and SVC are the ones that performed really well. I wouldn't say this is a pretty big data set as well, so it's pretty small. And you can see, so the time taken is also quite less as the data set is not that huge. And accuracies for CNN for different epochs is 96, 95. So the highest was around 96. Now the other SVC, since we are going to compare QSVC with SVC, I've again just written it down and kind of told for different kernel types what is accuracies and what are the time takens for each. So all this just basically tabulates what we have done and what are the results that we have achieved for each of them. So if you can see, QCNN performed like we got a 64% and CNN got a 96. So I would say one of the reasons why this is the case is because we used just 4 qubits and not like 30 qubits, even though if we had maybe selected like 10 features out of the 30 features, the performance might have been better. So due to certain limitations like those, we were kind of restricted. But if you see the QSVC and the VQC, they performed pretty well with like around 93%, which is pretty close to the classical machine learning. So that is one good thing that shows us that quantum has the capability that it can perform much better than classical as well with proper configurations and access to the hardware. So VQC gave around 81, which is also not bad. So this is again all about just more diagrams and representations. So like I mentioned, this is just a discussion of the results, what is that we achieved, and what are the basic differences between the two. So for classical reduced bits, and quantum is like qubits, and these are the basic concepts that have been used to do them. And again, this is all just tabulated. You guys can read through this. So conclusion of this is basically with access to more hardware, you can explore various things and experiment different kinds of stuff. So if you guys have observed or read recently, there has been a lot of news going on about quantum, of it being used in drug discoveries or in cybersecurity. All of these, it is also known that one of the algorithms can actually kind of sort of break this RSA, because the factorial time reduces significantly, which I had mentioned earlier. So that is one of the things. And they're also looking into like teleportation, how the principles of quantum can be used in such things. So that is one place. So there are a lot of applications where quantum is used today, and a lot of people are performing research on it. For example, IBM has always been leading in the quantum sector, and the other is like Google. So these people are like leading in quantum. So that's just a bit about what we had done. And this is how the data set basically looks like with all the features and the values. And so we have basically the normal machine learning case where we have done with all the features and all the algorithms. So just quickly skim through so that you guys can look at it. It is a basic machine learning pipeline with some cleaning, processing, and then tuning it. So this is how it looks for each of them, and I've just summarized it here. Same goes for all the splits. So I have also done machine learning with PCA so that we get like a better comparison. Even here we have reduced it to use more features so that we get a better understanding. Let's move to the quantum part of it. Okay, so the first steps are pretty much the same where we scale the data, we perform some pre-processing and standardizing the data, and this is basically just installing the Qiskit library to use it. And this is where I'm defining the different kernels and implementing the classical SVC first for different types to see what are the results, just for ease of comparison. Like I mentioned, we have something called a ZZ feature map, which is used to convert the classical features into the quantum states. So this is basically the structure as to how you have to do that. So I'm just mentioning the number of features I'm passing them, and then what is the type of entanglement that I want, and just building the circuit. So the circuit that gets built is called as ansatz. That is what a quantum circuit is basically called. Now, this is one thing which I mentioned earlier of using the simulator. So it's called as the CASM simulator. So this is how you would just import it. And now this is where we apply the quantum SVC and get the results. You can see the time taken and what is the accuracy that we have gotten, and also the execution on the simulator. So this is how it is. So a certain configurations or like the version compatibilities are quite different now, as this was done like around 3 to almost close to 3 to 4 years. So certain things have changed, and it might not run exactly if you guys try to run this notebook. So there might be few changes that you guys have to look into. So that is one thing, and a similar implementation for VQC. This is again applying the feature map, and it shows how it looks. So this is basically building that circuit which I mentioned earlier called as the ansatz. So like I mentioned earlier, we have gates like poly X, poly Y, poly Z. For implementation of quantum machine learning algorithms and in the deep learning, we have something called as rotational X, rotational Y, and rotational Z gates. So this is basically how you kind of tune what you call as parameters. So by tuning these, that's how you basically improvise the models. And by changing the different values, that is how. So those are the 3 new gates which are there in the quantum machine learning part of it. Again, you guys can have a look at this code. Like I mentioned, we use some optimizers called, for example, we have used the SPSA optimizer, and other is the Kobala optimizer. So you can use either of them, try in both of them and see which works better. This basically just shows the different circuits. Let's go to QCNN. So here how we basically define the convolutional layers, pooling layers. That's how we also make layers here. And you apply different gates. To kind of understand more about this, I would show you a page of quantum machine learning, which is provided by Qiskit itself, which gives you a better understanding of how you guys can go about. And I think now you guys have a lot of access to generative AI tools, which can help you understand better. So I'm not gonna go into like the entirety of it because it is it might get quite confusing. So I'll just show you a bit of. So this is how we've built the circuit and defined the convolutional layers, pooling layers. So this gives you a better representation. It's basically like how a neural network looks like. And now, if you can see here, we have used a different kind of optimizer called Escobila. So, and we're seeing what is the accuracy over the different epochs. Yeah, so that's about what we have implemented, and this is the resource that I was talking about, which gives you tutorial on quantum neural networks and quantum machine learning. I will also paste this link in the chat. You guys can have a look at this. So I think we have come to the end of the session. If I'm open to discussion, if you guys have any doubts, you guys want to know more about something, I will try my best to answer your questions.